Now, briefly summarizing what took actually quite a while to do here, and you know, the videos are fairly extensive, and if you can understand this more quickly, it's worth doing. We have this function, z equals f of xy equals x squared y, where now x is regarded as a function of t, cosine of t, y is regarded as a function of t. You see that function here, I don't have to read it to you. And we ask what happens if t changes from pi over 4 to pi over 4 plus 0.02. Of course, we could take our calculator and calculate the values of x and y at pi over 4 and the values of x and y at pi over 4 plus 0.02, put those values into the function, find out what f of xy would be if t was pi over 4 and what it would be if t was pi over 4 plus 0.02, but we'd miss all kinds of important insights if we just relied on the calculator. So what we want to do is we want to start with the effect of this change in t. So we start by evaluating the x function and the y function at pi over 4. So we get this value, which is really the square root of 2 over 2, and we get this value, which is really the natural log of 2. These are just decimal approximations that will stand in for those quantities, but we're going to use decimal approximations so we can see the numbers and kind of think of the numbers. Okay, so when t equals pi over 4 then, x is the cosine of t, which is this, so x is square root of 2 over 2. Now I've used square root of 2 over 2 here instead of 0.707. This is exact. And y is about 0.69, and that is an approximation. If I wanted to write the exact, I'd write natural log of 2, but we don't have any sense of what number that is. If we plug all that in, we get z approximately equal to 0.35. Just, you know, x squared, square this, y this, multiply them, we get 0.35. Okay. In 3 dimensions, that's going to tell us that if we have the 0.71, 0.690 in the xy plane, the coordinates of the pi over 4 point, that the value of the function, the z value, is going to be 0.35. Okay, you don't need to worry about the rest of this figure, we'll develop it. Okay, instead of just plugging in pi over 4 plus 0.02, we use what we know about derivatives and differentials. And that is simply that on a graph of x versus t, and this is a representative graph of the cosine, on a graph of x versus t, at pi over 4, the slope is equal to the value of the derivative. The derivative of cosine of t is negative sine t, so we evaluate the sine at pi over 4. We get, again, square root of 2 over 2. But since we have a negative sign, we have negative square root of 2 over 2, negative 0.707 approximately. That's our slope. Now we change t by 0.02, that's a run. What's the rise? Okay, along this tangent line, along this slope here, we find that the change in x is about negative 0.014. There'd be more decimals, it'd be 0.01414, just a couple more significant figures. That's not important for understanding what we do here. So now we see that a change of 0.02 in the value of t causes x to change by negative 0.014. And that was calculated by taking x prime of t, the derivative, the negative sign, multiplied by the delta t to get this. So on the picture now, we say, okay, positive x direction is this way, this is the negative x direction, and we're moving negative 0.014, so now we have this side of our usual figure. So the change in t gives us a change in x, which gives us this part of the figure, and we do the same thing with y. The change in y, we multiply the derivative, which comes out to be about 0.65 when t equals pi over 4, by the increment, and we get a change of about 0.013. So now we know that y changes by 0.013. Okay, so now we're in this figure. By how much does f change? Well, knowing how much x changes, how much y changes, we just use the partial derivatives to figure out the changes in z corresponding to this change in x, while y doesn't change, because y doesn't change along this segment. And then this change in y, which occurs when x doesn't change, and we're going to multiply that by the partial derivative with respect to y. To make sure we understand that a little better, we draw the picture. Okay, z versus x. When y equals 0.69 is just z equals x squared y, which is 0.69 x squared. That's a parabola. Okay, it's a parabola whose value when x equals 0.71 is 0.35 ballpark, within a hundredth, and could be calculated as accurately as we like. Okay, and then if we confine ourselves to the y, to constant y, we get a graph in a plane parallel to the yz plane. It's not the yz plane, but it's parallel to the yz plane through this point. And since x equals 0.71, which is really square root of 2 over 2, x squared is 1/2, and we have z equals 1/2 y. So the slope in the y direction is always 1/2 everywhere. The slope in the x direction in the vicinity of x equals 0.71 is approximately, where is it? I calculated it. 0.69x squared, the derivative is then 1.38x, and we plug in the 0.71, and we get the value of the derivative. And actually, it looks like maybe I've got that wrong, so recalculate that yourself. Because x is square root of 2 over 2, yeah, that slope is going to actually be closer to 1. So I think I messed up a little bit. I said the slope was 0.707 because I think I used the square when I calculated the slope. Okay, I think the slope is actually 1. Or very close to 1, just a little less than 1. Anyhow, okay, I've got an error on the slope there, but you can correct that. Okay, we understand then that in this direction, the curve is a straight line with a slope of 1/2, because the slope of z versus y in any plane, well, in this plane, is 1/2. The slope of the segment, and it's just a very short segment of this graph here, is, and remember x is increasing in this direction, so the function will go up in this direction. The slope is going to be, I'm saying it's going to be pretty close to 1. I'll correct that and do a brief addendum. So, just calculating, the rise here is 0.013. Remember, that came from y prime of t delta t over here, down here, times the 1/2, which is the slope in the plane parallel to the yz plane, this plane. So we get a rise of 0.065. We get a run that's the product of the slope and, I'm sorry, we get a rise over here that's a product of the slope and the run. And even though I calculated it incorrectly, we see that the run is the negative 0.014, which came from x prime of t delta t. The rise is, the slope is the 0.707. You multiply those together, you get the rise. And that was calculated, the rise, from the value of the partial of f with respect to x. So And we also, calculated the partials, see that we plug in the numbers and we do get what we're supposed to get, except maybe for this partial of f with respect to x, which I don't believe is right now. It might be. I doubt it. No, it isn't. Okay. Then in summary, we can say that our change in z is, first of all, this change plus this change, the negative 0.01 that we get here that we'll probably have to fix, and the 0.065, and I'm pretty confident of that, adds up to the negative 0.035. Now, what have we ultimately done? We've taken, again, this expression, which can be expressed as partial of f with respect to x, times x prime of t, but I wrote that dx dt, interchangeable notation, times delta t, plus the change due to the motion in the y direction, partial of f with respect to y, times dy dt for the y prime of t times delta t. It's all in this picture. Then, if we add these up, if we divide through by delta t, we get delta f over delta t is approximately equal to this. In the limit, as delta t goes to 0, this becomes exact, and this is then our derivative of f with respect to t. I've just got an etc. here, but the etc. is all of this.